So I said in a previous video that you could calculate the percentage distribution and equilibrium of the most stable to the less stable staggered form. And I wanted to just go through the calculation of the actual numbers. So let's consider butane. Looking down the C2C3 bond, and what we knew is that the 60-degree conformer, which is the one that had two methyl hydrogen eclipsings and one hydrogen-hydrogen eclipsing, was at 3.6 kilocalories per mole up. These energies are all going to be in kilocalories per mole. And the 120 degrees, which is the gauge conformer, is 0.9 kilocalories per mole up. And then the 180, which is the most unstable, that one's up to 4.9 kilocalories per mole. And then the 240 is identical to another gauge conformer. The 300 is identical to the 60, mirror image in fact, and 360 takes us back where we started. So we have an overall energy diagram that looked like that, where we had our least stable eclipse conformer with two CH3 groups overlapping here, where the energy cost was 2.9 for this one and 1 for each of these, for a total of 4.9. And two methyl groups in the anti-position here. And then at 120 degrees, we had our gauge conformer, where this methyl group is moved into this position. And at 240, we have the other. So the energy is the same at 120 degree rotation as it is at 240 degree rotation, because these two are enantiomers of one another. They are non-superimposable mirror images, and the 300 and the 60 we won't draw because we're not really concerned with that. So we have this equilibrium where we have our anti-conformation corresponding to, or in equilibrium with our two different gauge conformations, and we know that the energy gap for going from anti to gauge is equal to plus 0.9 kilocalories per mole. If we write the equilibrium constant expression, Q is equal to the concentration of the gauge conformer at 20 degrees divided by the concentration of the anti-conformer at 0 degrees. And we also know that the equilibrium constant is equal to E to the minus delta G0 over RT. And we're making two assumptions here. We are assuming that there's a negligible entropy change, which means that we can use delta H in place of delta G by assuming that T delta S term is negligible compared to the delta H enthalpy terms, because these are enthalpies. And we're also assuming that even though the strain energy, which is what we're measuring here, this 0.9 kilocalories per mole is a strain energy, even though the strain energy is not the same thing as the heat of formation, we're assuming that differences in strain energy are going to be comparable to differences in heat of formation, and with the neglecting of entropy corresponding to differences in free energy change. So we're going to plug in that number, that 0.9 kilocalories per mole. We're going to convert the kilocalories to joules by multiplying by 1,000 calories per kilocalorie and 4.184 joules per calorie. And then we're going to divide through by the universal gas constant, 8.314 joules per mole Kelvin, and 25 degrees room temperature, 298 Kelvin, that will cause all of our units to cancel, and we can actually calculate a number there. Come out e to the negative 1.52 and give us an equilibrium constant to two significant figures of 0.22. So we know that the gauge conformer divided by the anti-conformer is equal to 0.22, and the concentration of the gauge conformer will be equal to 0.22. Times the concentration of the anti-conformer. We have two gauge conformers, though. So we have three possible places that this molecule can be to be at a minimum one of the stable staggered conformations. So we also know that gauge 1, if you like, is equal to gauge 2, 120-degree conformer. Corresponds to the 240-degree conformer. And furthermore, we know that the concentration of the anti-conformer plus the first gauge conformer plus the second gauge conformer is equal to 1. 100% of the molecule is going to be in one of those most stable energy minimum. 0 degrees, 120 degrees, 40 degrees. And we know that the gauge conformer is 0.22 times the anti-conformer, so we can solve the concentration of the anti-conformer plus 0.22 times the conformation of the anti-conformer plus 0.22 times the concentration of the anti-conformer equals 1, or 1.44 times the concentration of the anti-conformer is equal to 1. And the concentration of the anti-conformer is equal to 1 over 1.44, which is equal to 0.70, or 70%. So 70% of butane is going to exist in this most stable anti-conformer, and the remaining 30% is going to be evenly distributed between the two gauge conformers, each at 0.22 times 70%, or each at 15%. So a total of 30% in the gauge conformer is evenly distributed between these two mirror images, and 70% in the most stable. The calculation will look a little bit different for the 2-methylbutane case. Because recall that in the 2-methylbutane case, rather than having one most stable conformer and two conformers that are somewhat less stable with an additional gauge interaction, we actually had two most stable conformers and only one at the higher energy. So for 2-methylbutane, we do the same kind of graph. Start with one of the most stable conformers, which is the one that has one of these methyl groups down here in the anti-position has just one gauge conformer, so 0.9 kilocalories per mole strain energy, just like the gauge conformer here. The other methyl group in that position makes no difference. And then that's in equilibrium. As we move this around, we move it to the 60-degree conformer, we'll see a situation that has 3 hydrogen over methyl eclipses. Moving this hydrogen up here. Each of those costs you 1.3 kilocalories per mole, so the 60-degree conformer is up here at 3.9. A little bit higher than the 3.6 here, because it has an additional unfavorable interaction. At 120 degrees, we're going to move this to a conformer that looks like this. Staggered conformation. This methyl group comes down. Got exactly the same energy as we had. And then it's going to be in equilibrium at 180 degrees. The conformation that has a methyl over methyl eclipsing at 2.9 kilocalories per mole, a methyl over hydrogen eclipsing for an additional 1.3, 4.2 kilocalories per mole, and then a hydrogen over hydrogen, which is 1 kilocalorie per mole, so a total of 5.2. And if we keep moving to 180, sorry, to 240, this, and now has two Gauss interactions, which means it'll be up to 1.8 per mole. So our curve starts to look like this. At 300 degrees, we will have an identical conformation with a methyl over methyl eclipsing, a hydrogen over hydrogen eclipsing, and a hydrogen over methyl eclipsing. So it will be out here. And then at 360, we're back to our 0.9. So we get a slightly different shape to our curve. We have two highest energy points, two lowest energy points, and one of each in the middle, one at 1.8 kilocalories per mole, and one energy, or sorry, one lowest energy, one highest energy, and then these two energies in the middle. So you might think that since there are two different ways of being most stable, we'll see greater than 70% of the molecule in the combination of those two. It's exactly the same energy gap, but now we have a situation where we have three different materials. Neither of those is anti or gauche. Right? This methyl is anti, this methyl is gauche, so you can't refer to it as the anti-conformation or the gauche conformation. But we can still say that the concentration of 1 plus the concentration of 2 plus the concentration of 3 is equal to 1.00. We can say that the concentration of 1 is equal to the concentration of 2 because the equilibrium constant for that reaction, the concentration of 2 divided by the concentration of 1, is equal to E to the minus delta H over RT, but delta H is 0. And if delta H is 0, E to the 0 is 1. And the concentrations are equal of the two equal energy materials. We know that delta H of reaction here, which we're saying is approximately equal to delta G of reaction, is equal to the same plus 0.9 kilocalories per mole when we're going to the Gauche conformer, which means that the equilibrium constant 3 over 2 is going to be E to the minus 0.9 kilocalories per mole per kilocalorie times 4.184 joules per calorie divided by 8.314 joules per mole Kelvin by 298 Kelvin. That's exactly the same set of numbers that we had before. And we'll give the same answer of 0.22 for the equilibrium constant. That allows us to write that the concentration of 3 is equal to 0.22 times the concentration of 2. So now we can plug this in. And we can plug this in. Concentration of 2 plus the concentration of 2 plus 0.22 times the concentration of 2 is equal to 1. 2.22 times the concentration of 2 is equal to 1. And the concentration of that conformer, Roman numeral 2, at 120 degrees is equal to 1 over 2.22. I believe that's equal to 0.45. But I will check. Yes, indeed, 0.45, which means 45%. So for 2-methylbutane, 45% of the molecule exists in this conformer. 45% of it exists as this conformer, and the remaining 10% is a methyl between the other two methyls. So in the case of butane, we have 70% in the most stable conformation and 30% in the combination of the two next most stable, the two gauche conformers. But for 2-methylbutane, we have 90% in the combined most stable conformation and only 10% in the less stable conformer. Okay. The difference is here there is one low energy point and two higher energy. Here there are two low energy points and one higher energy. That's why we see a 70-30 mixture versus a 90-10 mixture.